Assalamu alaikum warahmatullahi wabarakatuh. This is Shahad Rahman once again from the Department of Nuclear Science and Engineering at MIST. Okay. So in today's video, I'm gonna talk about very basic thing about depletion analysis. Like I will show you how the depletions are done and what kind of data you can extract out of a depletion. And I will talk very basic of this tool. So in today's video we're gonna run our depletion in a new scale in a core named a new scale power module, and the following data we're gonna observe today, like the K effective versus time, the K effective changes over time, like the first month of operation, what will be the K effective, the second month of the operation, what will be the K effective, and this way the 20th month of the reactor operation, what will be the K effective values, like will this K effective value be like less, will be decreased less than 1, or it will be more than 1 after even running in 20 months. So then we'll observe the K effective versus burnup, like the maximum burnup that we can get till the K effective value remains less than 1. And third, the isotopic concentration, like the uranium-235, which is the main contributor of a thermal in not modern reactor, like in most of the reactor that you see is basically utilized this uranium-235 wells. So over the time the concentration of uranium-235 will decrease. Why? Because uranium-235 will cause fission, and day by day the concentration of uranium-235 will decrease, but the other product, the fission fragments of uranium-235, will increase day by day. And like the xenon, which act as a reactor poison, we can see the concentration of xenon 135. Yeah, so we can see this thing. And last two things, like the normalized flux per assembly and normalized power per assembly. So if you see the core, this is actually the core in which we will run our depletion. So we can see like we can calculate the flux generated from each of these assemblies and the power generated from each of these assembly as well. And I'm saying this normalized because by default OpenMC gives us a normalized data like in units of per Newton particles. So like if OpenMC give output, if you extract flux data out of OpenMC, by default it takes source strength as 1 Newton per second. So the unit of flux becomes per Newton source particle. What happened? আমার ম্যাক ভয়াবহ পাগল হয়ে গেছে, ওরে এত পরিমাণ ইউজ করা হয়েছে। এখন 3-4 মিনিট আগে ইনস্ট্রাকশন দিছে, তখন সে আমাকে ওইটা শো করতে পারে না, এখন সে করতেছে। আমার সিপিইউ স্লো হয়ে গেছে। আমার সিপিইউ স্লো হয়ে গেছে। কষ্টে কোথায় কই যা লুকাবো। Anyway, so in today's video in today's core, this reactor core will contain like it will be constructed with 7 type of fuel assembly like that, and this 7 type of fuel assembly will be categorized in 3 types. Like I will categorize them in 3 types. Like one type of fuel assembly will carry the twice burned fuel, and B type like other assembly like B will carry the once burned fuel, and C type will carry the fresh fuel. What is meant by this twice burned, once burned, fresh fuel means like this new scale core is considered to be with reactor cycle length of 2 years. Means once burned means the reactor will be operated for 2 years continuously, and after that 2 years it will complete its one cycle, mean once burned. So first of all, the how so once burned mean one cycle is completed, and twice burned mean two cycle is completed. Each cycle is 2 years. Okay. And fresh means fresh, like the fuel is not go through isn't go through it in. Fresh means the fuel is never faced any nuclear reaction. Okay. Then come to this page. This pic is showing you the position, the assembly, individual assembly, where the control rods are like contained, the assemblies containing control rods. And in today's video, the control rod state will be like 100% withdrawn, means the control rods isn't inserted inside your reactor core, they are in 100% withdrawn position. Okay, then this thing we'll talk about this later. আমরা এটা নিয়ে পরে কথা বলবো। আমরা যে ইন্ডিভিজুয়াল পজিশনে যে ফ্লাক্স ভ্যালুগুলো পাচ্ছি, ওই ফ্লাক্স ভ্যালুগুলোকে আমরা এই সব জায়গায় কি বসাবো। এইখানে একটু ভুল আছে, এটা আমি একটু ঠিক করি। There are some mistake, like, and this will be C02 and C02. Also some mistakes. Okay, anyway, maybe this is A01 PC. Anyway, so, and in today's video we're gonna use flux tally score and heating local tally score. Flux for flux value and heating local will be for power calculation, and two distinguished filter will be used for each tally. These are dispersal filter and energy filter for very accurate calculation. So let's go. Let's type Safari. The Safari. So this is where we will go today, and you see my code is already created here. So anyway, this is how my code look like. You see, this is the code that we will run depletion on, and this is spacer grid, this is spacer grid, this is spacer grid, and each color is correspond to a different assembly. Okay, so this is one assembly, another assembly, another assembly, another assembly, another assembly, another assembly. Okay. And this is one kind of fuel this is one kind of fuel assembly, and in today's video I'm gonna use two type of very specific fuel assembly. One is type 1 and type 2, and type 3 and type 1 is like same, like they are same in configuration. So you can see here the red cells are basically guide tube, and in center the red tube is basically the instrumentation tube, and the yellow color they are gadolinium mixed fuel. Type 1 assembly like A01A, B01, C01, they are not containing those fuel assemblies, those are having gadolinium mixed fuel. So this fuel you see, this fuel rod you see, they have no gadolinium inside it, but they have this yellow color has gadolinium inside it, and they have this each assembly has 17 in rows and 17 in column, means 289 number of fuel rods is used inside, like not fuel rod, like lattice point is present, 289 lattice point is present in each assembly. If the normal type 1 fuel, normal type 1 assembly has this guide tube, means 289 minus 25 means 264 fuel rod. but the fuel type 2 fuel rod, which is containing the gadolinium mixed fuel rod, so they have 16 more fuel rod that is having gadolinium inside it. So if I ask you that in type 2 assembly, how many fuel rods having gadolinium in, how many rods are containing fuel, normal fuel, gadolinium mixed fuel, doesn't matter, but how many fuel rods are containing how many rods are containing fuel, you have to say 289 minus 25 means 264 fuel are containing fuel rods. Doesn't matter it is normal fuel rod or gadolinium mixed fuel rod. Then the distinguishing between type 1 and type 2, like in type 1 the 264 fuel rods are having no gadolinium inside it, but type 2 are having 16 that type of fuel rods that having gadolinium inside it. So you have to subtract 16 more fuel rod to have the number that's containing the type 1 type of fuel. Okay, so it is 248 fuel rods in type 2 assembly that's having normal fuel without any gadolinium inside it. So these are the very basic thing that you have to remember today and to run depletion work. Okay, and you can see for like saving our time, I kept the batch number 10, inactive batch 5, and particles number of particles is 1000 per batch. So this inactive batch 5 means it actually OpenMC, what OpenMC does, it gets a k effective value, then it converge, actually it converts toward the exact k effective value. But okay, so inactive means inactive batches help OpenMC to guess a initial k effective value, and batch number 10 means it actually iterate this k effective value for 10 times. So more iteration means more accurate value, more particles per batch means more accurate value. Okay, so more particles per batch means more accurate assumption, initial assumption. So more accurate initial assumption means you are more closer to your actual value by iteration, doing iteration. And then then come to the source. We are using independent source. And why we are using independent source, because you can see the core is very symmetrical in looks, in shape. So at this kind independent source work very well. Okay, or point source work very well as well. Or otherwise you have to, if this is asymmetrical, then you have I prefer using the spatial source, a spatial distribution. Okay, and the setting is done now. Okay, আমার তোমাদেরকে কিছু বলার আছে, লাইক আমার তোমাদের কাছে কিছু ক্লিয়ার করা আছে যে এই যে ফাইলটা, আচ্ছা এটা না, আগে বলি যে first of all that in today's video I'm not gonna show you how you have to recreate this code, because you can see there are, if I show you the lines, there are 1332 lines for materials and that I typed, and 1443 for my actual geometry. So it's unrealistic, like this will not happen that I will put these lines in front of you. So what I'm gonna do, I will post this code that you can further use this. You don't have to like waste your time in recreating this geometry. I will just provide you freely without any cost. Then তারপরে দেখ এখানে একটা ফাইল আছে যেটা আজকে তোর ডিপ্লেশনে কি ইউজ হবে. This file you can see this carries the nuclear chain reaction data, like if uranium 235 goes through fission, or what kind of fission fragment it will produce. So it carries the chain, the nuclear chain. You understand what I'm saying, right? So this is 958.5 kilobyte. So this is very light file, right? Like it isn't even 1 megabyte in size, but because this is simplified chain for thermal spectrum, because my reactor works in thermal spectrum, means my reactor best utilize the thermal neutrons. Okay, so আমার যে reactor কোডটা আছে এটা thermal neutrone চলে, মানে এটা যে criticality ensure হয় এটা thermal neutrone. So that's why I choose depletion chain. You have to write this to get this page. You have to write OpenMC depletion chain. So you will get this, and in this there are 4 individual files, not 4, there are 6 files. 2 are for older version, like you can see this is 7, this is 7, and this is 8, same name, but this is 8, means this is latest. And this is for thermal spectrum, for the reactor work in thermal spectrum, and this is for acoustic spectrum. And then simplified chain, I'm using this actually. Okay, for as my OpenMC version is 0.15.2 maybe, means the most latest, and that's why I'm using I have downloaded this, not this. Okay, so if I downloaded this, and if I had downloaded this, you will see the size of the file. Like this is simplified, but this is not simplified. This is the very big data file. You can see this is 27.7 megabyte in size. Then come, so there are 10 batch 5 native. Now I need to define some tally to get the flux data and the power values. So how do I do that? I specify some tally. So tally, how to do that? I say OpenMC dot tally, and I give it a name. So what should be the name? The name is like A01. Like I told you, I want flux for each of the assembly, so I will specify tally for each of the assembly. Okay, so I will say A01 assembly uni. Okay, so okay, this is done. Basically I want this name. Oh god, this is why keep this 2 names same? Cause I don't want to share why I'm doing this. Okay, this is hot. Anyway, this is the name. This is for this tally is going to collect data for the assembly universe, like the assembly type, this assembly. Okay, this 4 position. So I have to say T1, you got the filters, and like the filter will be energy filter. So I have to create energy bins and energy bins open. Okay, so this is 0 to 20 mega electrovolt. Okay, 10 to the power 6. Okay, so this is 0 to 10 to the power 6 mega electrovolt, and energy filter. Okay, I have to write OpenMC dot energy filter and give it the energy bins. Okay, energy filter. Okay, fine. So filters are energy filter that I just created, and distrib cell filter. Actually, OpenMC dot distrib cell filter, OpenMC dot distrib cell filter. So this distrib cell filter needs the name for the cell that's containing the actual fuel. So this I'm collecting the flux value, the power value for individual assembly. So this is just a name of the tally, but how do I make this tally know that I want the data for this assembly actually? So I have to put a name of the cell that is inside this assembly. If I show you, if I go further, you will see this is that assembly universe, and this has a cell that is actual cell that's containing the actual fuel. So a cell has multiple fuel rods, and multiple fuel rods has multiple components. Like they have top nozzle, that the top nozzle has no fuel inside it. It has upper plenum, in cap, lower plenum, bottom nozzle. These are the component. So these are the component, and they have a specific part that's containing the actual fuel, and this is this cell, and this cell has a name A01F CLF. And if you see, I kept this name very common and very similar to this. Okay, if this is A01 PC type assembly, then the name becomes A01 PC FCLF, and this repeated for each of the assembly. So now I have to put this type of name, whatever in this part. If Shahid, this name is in this part. If there is no MB02 FCLF, if there is Shahid, then you have to write Shahid here. Okay, so you have to put the cell of that assembly. So what was the cell name? The cell name was like, let's copy. I kept this name very similar for all of the assembly. So this is the cell that is correspond to this assembly. Okay, now the tally will contain every flux inside this fuel. If this fuel is 264 times in that assembly, it will carry the 264 flux value, power value inside this T1 tally. Okay, now let's give it some score, that what kind of data we want. So we type T1 dot scores is equals to, like, we want flux value. So flux, yeah, flux value. So I say flux, and then you better type heating local for better power calculation. Okay, and heating local. Okay, heating local, and these are the thing that I want as a tally data. So for A01 assembly, defining tally is done, but you know, I want tally data for each of the assembly. So what I have to do, I have to repeat this for 8 times, cause A01, we have A01, we have A01 PC, we have B01 PC, we have B02 PC, C01 PC, C02 and C03. Okay, so I have to do it for 8 times, like 1 2 3 4 5 6 7 8. So now I have to give it a name, like PC, the actual name. So B01 PC. So this is B01 and this is PC, and then B02 PC, B02 PC C, oh god, A02 PC. This is A02, oh god, this is A02 PC. Then it comes on B01 PC, yeah, then B02 PC, B02 PC, and then C01, then C02, then C03. So but each of that assembly has to be that each fuel type. Okay, the name of the fuel is inside this assembly. So I already told you the name is very similar, and you can type just C03, you can type C02, and you can type, because this name is already given, and I already show you how these names are written. Okay, C01 and B02, and then B01 PC, B01 PC, then A02 PC, oh god, A02 PC, A01 PC, and then A01. So defining the 8 tallies is done. Now I have to put all the tally inside a tallies file, okay, to export it into XML file. IES tallies equals to OpenMC dot tallies, yeah, third bracket, you must use third bracket. So I have to write T1, T2, T3, T4, T5, T6, T7, and last but not least T8, and convert it into export by dot export to pro. আমার বাসায় সিউসাম ভুলেই গেছি। So exporting tallies is done. Now what I have to do, I need to run depletion. So depletion requires two things. It requires one thing, it requires integrator, and integrator requires four things: power, time steps, time unit, and operator. So for creating an operator, you need two things more. One is chain file, the depletion chain that I already show you how to download, and another one is a model. So model is like this: OpenMC model. You have to put the materials that you created. Materials is equals to materials, geometry is equals to geometry, tallies is equals to tallies. You see, the name has to be same, okay. Then it comes on settings is equals to settings, it comes on settings, god, alhamdulillah, geometry, tallies, settings, okay, geometry, okay. So model, defining a model is done. Now I have to do that all the nuclear fuels, I have to give input, all the nuclear fuels volume. I know the fuels that is used in my core, like the name was, I memorized it because I give too much time to create these materials, okay. So I say once once uranium oxide type 1. So type 1 means it is either A01 or B01. It can be C01 because C01 has fresh fuel. It has no once burned fuel or twice burned fuel. So how did I get those once burned composition and twice burned composition? Because basically my core, you see the core, each assembly of this core was containing fresh fuel. Like this fuel hasn't been faced to any nuclear reaction. So the fuel was very fresh, and I ran depletion on this fresh fuel configured core, and depletion was run for 3 times 2 means 6 years. And after 2 years, as the 2 years refers to once burn, after 2 years it I gave instruction to my while I was running depletion. I will show you how. So I gave it instruction to, after 2 years operating, it will give me a file that will carry the nuclear composition that is present that time, and after 4 years it will give me another nuclear materials composition file, and I will make use of that composition again. Okay, so what I did, I ran depletion for times 3 means 3 times 2 6 years. It ran for 6 years, and after 2 years it gave me a file, and after 4 years it gave me another file. Okay, and I utilized them as the materials. Okay, so this is fuel, and what is the volume of this fuel? So type 1 assembly, I show you type 1 is how a type 1 assembly look like. The oh shit, assembly is not defined. B01 assembly is not defined. What do you mean? B01 assembly is obviously defined. Oh, I see. So what I have to do, I have to run it for once. Oh god, I have to run it as well. You see, this is taking too long. Tally. Oh god, no. Okay. I'm not gonna see what I do. I will tally. I will say tally. Okay, now this is gonna work. A0 to PC doesn't exist. Okay, A0 to PC doesn't exist actually. So this will be only A0T. A02. What nonsense! Oh god. কি অবস্থা, খেয়ালই করে না। এবার অতিরিক্ত মানে এত বেশি কেউ গট করে, মানে এটা কি যায়? অভ্যাস হয়ে গেছে ভাই। আল্লাহ মানুষ তো। আল্লাহ আল্লাহ মানুষটা আল্লাহ আল্লাহ করবি গড়গড় করছে so this is done now জানে মেরে ফেলাম যদি এখন না ইসা যেটা চাইছি ওইটা তো দিল না গাধা okay this is type 1 and all the type 1 all the assembly of type 1 this is called all the assembly of type 1 has the same configuration like 25 guide tube like 24 guide tube and one instrumentation tube in the center and the other rods are fuel rods so there are 264 fuel rods so A01 type means there you will get 264 fuel rods and if you know that if this is A01 type of assembly and it is repeated for 8 times means you have fuel rods 264 times 8 and if you know each fuel rods volume then you know the fuel inside these fuel rods you know the volume of that fuel so this is my approach this is how my approach will be so I will know the type which assembly is using this fuel and as I know once burn fuel is using only B type assembly and type 1 means B01 type of assembly so if I search for B01 you can see we have only this assembly okay B01 type of assembly is 8 times repeated over the core so I will say 8 multiplied by 264 as this is type 1 assembly and it has no gadolinium mixed fuel so it has 264 fuel rods and each of the fuel rods volume is 103.46 where's my calculator okay so how did I calculate it the radius for each of my fuel rods was 0.4058 so 0.4058 is square times pi times 200 centimeter why because the length of the fuel rod not the fuel rod the particular height that's containing the fuel is 200 centimeter so this is saying 103.46 so I will say 103.46 multiplied so this is its volume and let's come on to its খালাম যদি এখন কইছে স্মার্ট মোড anyway so এটা হচ্ছে type 2 so if I say once uranium oxide type 2 is utilized by B02 assembly you shouldn't mind because B assembly using once burn fuel and type 2 is B02 you see B02 is this assembly so this is assembly and this is 4 times repeated over the core so we have to multiply it by 4 and each assembly is having fuel you see this is type 1 and this is type 2 and this fuel assembly has 289 lattice point 25 of them is guide tube and central instrumentation tube and 16 of them are gadolinium mixed fuel so normal fuel means this type 2 fuel has no gadolinium in it so without gadolinium there is 289 minus 16 minus 25 means 248 fuel rods so this is 248 and then comes on the type 2 but gadolinium mixed fuel so this type 2 fuel assembly has gadolinium mixed fuel rod and the fuel inside is once burn uranium oxide type 2 GD as I remember so this is actually this if I show you the proof that it's actually available মাথায় নষ্ট হয়ে যেতেছে মুখ দিয়ে কি বেড়ে গেছে তো আমি যদি তোমাকে দেখাই যে এটা হচ্ছে সেই ফুয়েল, ঠিক আছে। তো এইগুলো 4 times 248 times 248 হবে না, 248 না 16 হবে, বিকজ ফুয়েল রড প্রতিটা অ্যাসেম্বলিতে কয়টা করে, 16টা করে। ওকে, then comes on the twice burn flow, same. Okay, so once burn will become twice burn, TWIC, twice burn uranium oxide type 1. So twice burn is utilized by assembly A, and type 1 means A01, and you can see A01 is 4 times, and A01 PC is also 4 times repeated. So means that twice burn uranium oxide type 2 is used in 8 assembly. So this will become 8, and each assembly has 264 fuel rods that's having no gadolinium inside it, and each of the fuel rods become 103.46. And then type 2 becomes for type 2, that fuel is in A02. So A02 means this assembly, and this is repeated for 4 times. You see, this is for 4 times. So 4 will be multiplied by 248 because 16 is gadolinium mix. So normal fuel is 248, so this is as usual. And type 2 in gadolinium mix, same, you already know the explanation. And then comes this. So uranium oxide type 1, this is a fresh fuel, and this is in C01 assembly, and I show you this is repeated 8 times in the core. You see 6 and 2 means 8 times repeated in the core. So 8 will be multiplied by 264 times 103.46, and then type 2 means 4. You see, you need the proof, right? So there it is, there is 4 times repeated this assembly. So 4 multiplied by 248 times 103.46, and then type 2 but gadolinium mix means 4 times 16 times 103.46. So this is defining volume of individual fuel that will be depleted over time in depletion. And OpenMC will take care of their concentration over the depletion. And then your model is done. So for creating your operator, you need model and your chain file. So chain file, chain file means this name actually. So by so this is your chain file. Now you have to create your what is texting me. Anyway, so we have to create that operator, right? So we will create that operator. OpenMC dot deplete. So so I have to import depletion first. Import OpenMC dot deplete. Okay, now I can use this input OpenMC dot deplete. Okay, fine, dp personal deplete dot coupled operator. So PLET coupled operator. So coupled operator has model coupled operator, and it has model equals to model, and it has chain file. So the chain file is just defined. Okay, so creating mod operator is done. Then it comes on the integrator. integrator, very easy. Integrator OpenMC dot deplet dot predictor integrator predictor integrator, and this integrator require 4 files like your power. So you have to say Allah Akbar. 160 megawatt thermal cause the reactor we are using today new called power module. Its thermal power is 160 megawatt thermal power. So we have to say mega. So power is 160 megawatt. Okay, and then time steps. Time steps means 30 days times 20, then operator okay, then time steps unit actually. Time steps time step unit আমরা ইউনিটটাকে নিব ডেতে, মানে 30 দিন পর পর সে হচ্ছে কে এফেক্টিভ হিসাব করবে, তারপর হচ্ছে সব কিছু হিসাব করবে হচ্ছে কি 30 দিন পর পর, এবং 30 দিন পর পর কি সে একটা করে ফাইল দিবে. সো আফটার এভরি 30 days it will generate a file and the file will be shown up in here. Okay, so time step unit in days. So if this is done, if means you're ready to run depletion. So what you have to do, integrator dot integrate integrator dot integrate. Okay, so it's saying volume not specified for depleted material with ID 7 name 4.05 uranium 235 uranium oxide. So আমরা কোনটার ভলিউম স্পেসিফাই করি নাই বলো? C02 ওকে, C03 এর তো ভলিউম স্পেসিফাই করা হয় নাই. C03 is like 1 times 264 times 103.46. I guess this is gonna work now. This is very painful. What I have to do, I have to restart my kernel. I will shut down my kernel. It's not kernel, it's kernel. Perfectly it will run now, 100% sure. খায় ফেলতে মন চাচ্ছে না. কোনো সুযোগই নেই এখানে ভুল হওয়ার। You can see okay, first problem is with ID7. This is that ID7, and as far as I remember, I have given it a volume. I have given it a volume. Of course, you don't know set type 1. What else you want? What is it? If you're saying volume not specified for depleted material ID7, what nonsense. Here I can say this is defined here. Delete them. Understand what happened. Now the problem with Docker. Okay, I have to quit and come again. Yeah, that I have to do, because I see no problem with anything that I defined. My CPU is super slow. I didn't want it. Now this is gonna work for sure, 200%. Again. Where's the problem? God, that খেয়ালই ছিল না। I have to define this more, this thing after. This is problem of Docker, not mine. Motherfucker Docker. Anyway, so this depletion will take too long, like it will take like around half 1.5 an hour, like 1.5 hours it will take. So what I'm going to show you that I have already ran this before and collected data inside here. So all the data you can see here you will get in here. Okay, so what I will do, I will just copy all the data here and I will copy all the data. So what I will do, I will copy all the data and paste it here. We'll paste it directly here. So I got all the data that will be found from running depletion here. Okay, so what I will do now, I will do everything that I promised you. Okay, so first of all, I think I need to show you key-picked values versus time. So how we do this, you see there's a depletion dot result, where is it? Okay, here it is. Depletion results.h5. This file is containing all the data you can see here. So how these files are generated, you see we gave a command like 30 times 20, and you see there's number 20 and there is 0, means it has generated 21 files, and initial file that is generated by a node, it carries no depletion data. Okay, it is initially just simply if you run openmc.run, it will generate the same file that is generated in here, and then it comes anyway. So all the data you see, everything is like you can get them from this file. So if you delete all the files without this summary.h5, this is very important. Okay, like if you extract any tally data from this .h5 depletion results file, and you want to see this in pandas data frame format, you need this summary.h5 file. And for your betterment, I wanna let you know that minimum step size, like this is step size. Okay, this 20 number is step size, so this has to be minimum 3. Okay, like if you give it 2, then this will not be any effective data for you, and this has to be minimum 3. Why? Because if this become 2, then this file and this file will carry the same data, means depletion will not occur, but it will take your time. But if you give it minimum 3, it will carry this data will not carry any depletion related data, but this and this will carry depletion related data. Okay, and you will get this 4 file that time. Okay, so anyway, this was 20. Now I need to see the k50 value versus time. So we can do this by doing this. Result is equals to openmc dot deplete dot result. Okay, results. So here you have to put this name. Okay, what is its name? Depletion results dot h5. So you have to write depletion results dot h5, depletion results dot h5, and then what you have to do, you need the time and k effective data. So you have to write time and k effective data is equals to, you have to write result dot get k effective. Okay, if you do this, you will see, like if I print time and k effective, you will see like opens. Okay, fine, I understood. Import OpenMC, because the kernel got shut down while we were doing coding. So import, you have to write import OpenMC. This is not necessary if your kernel was never shut down before. Okay, I have to import this as well. Import openmc dot deplete. You motherfucker. Sorry. Anyway, so these are the time, and these are the corresponding, these are k effective values. Basically this is k effective values. Yeah, like if you delete this, you can see the k effective values. See, this is k effective because the last one is printed. And then if you type time, you see the times. Basically this is 0 days. This is if you convert 30 days into second, you will get this. If you convert 60 days into second, you will get this. If you convert 90 days actually into second, you will get this. So as you instructed 30 times 20, so this is showing all the times when the files were generated and the corresponding k effective values here. Okay, see this, what I did, this is standard deviation, very high standard deviation. Generally when you are calculating with OpenMC and you are calculating k effective, means k eigenvalue you are doing k eigenvalue calculation, the standard deviation must be less than 0.0001. okay. Oh god, this message isn't from any human being, this is from Ludo King. একদিন ফেসবুকে খেলছিলাম, ওইখান থেকে এখন ডেইলি মেসেজ দেয়, মানুষ না, অ্যাপস। So you can see the standard deviation means the values you get in here is very inaccurate. Like normally what happens, from the day 0 to day 100, the k effective value has to decrease. But if you plot k effective versus time in here in this calculation, then you will see in some days, in somewhere in the middle of beginning to the end, in somewhere k effective becomes has risen actually. Okay, so this is what happens. That's why the batch number has to be it has to be increased, and means the active batch and the inactive batch as well. No, this is not what this was like this. Okay, this is what we ran actually, this is what we ran, and the batches were 10, the inactive batch were 5, and the particle were 100. So if the inactive batch become very less than OpenMC, the problem is in that case that OpenMC failed to guess the initial k effective values very effectively. And if the batch number is very small, then it fails to convert its initial fails to convert to the main value. You know what is iteration. If you're from any engineering background, you know very well what is iteration. So in iteration, what we do, we guesses a value and then we try to convert with certain conditions. So OpenMC does the same. So inactive batches are used to guess the initial k effective value, then it converts over the batches number and increasing the particles, the initial guess, or whether you say initial guess or whether you say the convergence efficiency becomes risen. Okay, and what I was talking anyway, so I got time and k effective value. Now easily we can plot them. How? Like you can easily say import matplotlib.py plot as plt. Now you can write plt.plot, and in x-axis there should be time, and in y-axis there should be k effective values, first value, like not standard deviation, only the mean value. Okay, so if we do this, then you will see a plot. Okay, you see in some place the k effective has become rising. This is totally unreal, like this cannot be happened. Okay, this is, if I show you in this position, in this peak, the how big the error is, you will just be disappointed. Like if I just type error is equals to k effective কি হবে k effective no k effective ভিতরে লিখতে হবে 1 ওকে এটাই I think I should split it. Where is split? Okay. Okay, so I have to write error bar. So if you can see this, right? 100% you can see this, the size of error in each of the peak. When OpenMC calculate the effective value in here, the error was in this size, and the maximum error where it is found in here. You can see the maximum error is in here, very big error. So it fails to calculate the effective value just because the active batch was very small, inactive batches was very small, and the particle number was very small. For the core was very big, right? It's a very complex geometry. So for a big and very complex geometry, these particles has to be very high in numbers, and the active batch, inactive batch, they has to be very high in number. So then this is how you see the k effective value over time. You see the time is in 10 to the power 7 form, because these are in second in x direction. So what you can do, you can just convert the time into second. How do you do that? I do time is equals to time divided. What you can do, actually you can just write time is in seconds, so divided by 86,400 seconds. So it will give you time in days, like 600 days. If you multiply 20 times 30, so it will give you 600 days. You remember the 30 days and multiplied by 20. So OpenMC ran this ran your core calculation for 30 days times 20. Okay, so for 20 months it has calculated the k effective values. So there the time is converted into second. If you want to see, this is actually k effective versus time in days. So you can just say like plt dot x level, oh no let go, plt dot title, title title. So this is k effective versus what, time in days, k effective versus time in days. So this is what we got. If I take a screenshot, let me take a screenshot. Okay, and this is k effective versus time in days. If you want k effective versus, like this first one is then k effective versus burnup. So how do you get K50 versus burnup. So you have to convert this time into burnup days, but into burnup actually. So what I do, I say time is equals to time. So you see the burnups unit, this is gigawatt day per metric ton unit. So I have day, I have to convert it into gigawatt day. So what I have to do, power multiplied by day, power has to be in gigawatt, then the power is, if the power is multiplied by day, then the day will be converted into gigawatt day. Then if you divided it by the mass of your total fuel, and if your mass unit is in metric ton, then you get the time converted into gigawatt day per metric ton unit. So how do you do that? I say time, you have to convert it into day, so you have to divide it by 86,400, and time has to be multiplied by 160 megawatts. So if you convert it into gigawatt, then you have to divide it by 10 to the power 9, then you got 0.16 gigawatt. So 0.16 multiplied by time divided by 86,400, and if you divide it by the total mass of your fuel, so how do you get the total mass of your fuel? If you see the if you can calculate the total volume, then you can convert it into mass actually. So how do you do that? I have calculator, I will calculate the total volume. So what I will do, 8 times 264 times 103.46, okay, it will be this plus 4, okay, plus 4 times 248 times 103.46, then plus 4 times 16 plus 103.46. okay, these and these are same, so if you multiply this by 2, then I add this one too. So plus 264 103.46, okay, so I got 1010597.28 gram. So how do you convert this into, sorry, this is volume, means in centimeter cube, so you have to convert this into grams. So how do you do that? You have to multiply it by the fuel density. Let's say this is, suppose that, let's say this is 10.5, so I multiplied it by 10.5. now this is in gram, so I have to convert this gram into metric ton unit. So how do I do that? I divide it by 1000, so it converted into kg, divided by 1000 again, it convert into 10.61 metric ton. okay, so 10.61, so metric ton, so fuel mass comes 10.61 metric ton unit. okay, so I have to write 10.61. so the time is converted into megawatt day. Time is converted into megawatt day, sorry, no, megawatt day per metric ton uranium. So if I now do this, oh god, no, this is done. If I, what is happening? So now, okay, there should be time. Okay, you see. No, no, megawatt day. Zero 0.6 on time. Megawatt day. Okay, now we got it. So you can see now k effective versus time. We on say this is time. We will say megawatt day per metric ton uranium. So if you plot it again, so this is k effective versus megawatt day per metric ton uranium. So there you can see this is nonsense. Okay, this you can see this is 8 megawatt day per metric ton uranium. Okay, this is very high. So let's take a picture. So we took a picture of that. Then so our number 2 task is then isotopic concentration over time. How do we see the isotopic concentration changes over time? How do we do that? We do this like we say time and the variable, the concentration, anything, any variable. So what you have to do, you have to write result dot get atoms, atoms. Okay, atoms, and there you have to give, if the material has any ID or any name, you have to give it under this material, that ID or name. So the material ID is like, I will give it like, let me show you something, let me teach you something, that if you see the material, I wanna see the uranium-235 concentration over time, like how its concentration changes over time. So what OpenMC does, OpenMC accounted for the concentration of uranium-235 for each type of the material. Like under this ID, it has recorded the concentration of uranium-235. Under this ID, it has recorded the concentration of uranium-235. So if you wanna see the concentration of uranium-235 over time, you have to mention under which ID you wanna see the concentration changes over time of uranium-235. So you have to mention material ID like 1 and say the nuclide name under nuke, and nuclide is like, I wanna say uranium-235, so U-235 concentration, I wanna see that. And let's say the density, like nuclide density or concentration unit should be in atom per centimeter cube. Let's say this is cold again, so let's say unit is in atoms per centimeter cube. Okay, and then time unit. Okay, time unit is in, let's say second, no, day, of course day, time units should be in day, let's say. So then you can again plot in the same way, like plt dot plot, and in x direction there should be time, and in y direction there should be concentration. You can label, you can give it a title like plt dot title, and the title name should be no, not effective concentration. This should be concentration of U235 235 versus time in days. So you see, so it's saying a unit should be in atom per centimeter cube, atom per burn centimeter cube, or atoms. So it can be atoms per centimeter cube. So this is the concentration changes over time of uranium-235 in under ID1, like the once burned uranium oxide type 1 fuel. So if we give it a ID say 20, you see this is changed a little bit, and if you give 3, this changes a lot, and then if you say 4, this changes a lot, right? And if you give 5, and you see like that, and means the trend is very similar. Okay, this is very much change. And then if it is 7, you see this. Okay, then let's say 8. Okay, let's say 9. I'll show you something now. So this is 9. See, you see. Then let's say 10. You see. Let's say 11. Okay, now when you are giving material ID 11, this is showing an error. Why? Because under ID 11 there is no nuclear name uranium-235 that was depleted, or you specified depletable true. So what did I mean actually? I mean that by default the fuel containing uranium related uranium are generally depletable. By default it is depletable, means the depletable said to be true. We don't have, if we don't write this line, by default it will take it as a depletable too, and then when we are running depletion we have to specify the volume of that individual materials. But if I show you the ID 11, where is it? This 16, 14, 13 till, and this is ID 11. This is zircon 4. So do you think zircon 4 will contain any uranium-235? So why not this error will occur? Okay, error will definitely come on your screen. So this is what happened. Now we'll take a snap actually. Okay, so say screenshot. So this is a very beautiful screenshot I'm gonna take now. Okay, concentration versus time in days is done, and then a normalized flux per assembly. How do you do that? This is very interesting. How do you do that? We get the tally data. So first of all we have to read the state point file that is generated in here. Where is it? This is in here, that state point for a point 10.h5. Why not in this? Because we didn't run depletion on 100 batch. If the batches number was 100, then the file would be this. You are seeing these two files because previously I generated these files just to save some times. So what I have to do, I have to read this file first. So how do I do that? I say OpenMC dot state point, and there you have to state point, you have to give the exact name that I just show you, 10.h5. so state point file has been read. It's taking 9 seconds. Unbelievable. $11 it took to read this statement file. Unbelievable. It would take like 2 to 3 seconds at the very beginning. Oh god, hilarious. Anyway, so the tally you see, the T1 tally was for the A01 assembly. So what I have to do, I have to take this tally data back. So I will say tally, suppose T11, any variable you can say T1. You can also say the T1 that is previously defined before. Okay. So what you have to do, you have to say sp dot get tally, and there you have to give it a name, that which tally you do want. Actually, what is the name of a tally that you want from statement file. So as I want tally data for this assembly, A01 type of assembly, then I have to give the tally's name. So the tally is here, and then the tally data is carrying two data, flags data and heating local. So I have to distinguish these two individual. So I have to say sp dot get slice. So get slice, what it does, it actually create tally from a tally. Okay, so get slice, you have to give it a scores, that which scores data you want. Actually I want flags, and then I want, so what it's doing actually in these lines, what this lines doing, if I show you A01 assembly, A01 is 1 2 3 4 5 6 7, that means 1 2 3 4 5 6 7 8 times repeated in 8 individual position. A01 assembly is present. So what it will do, it will take all the individual flux value, like this assembly has 264 fuel rods, so it will get 264 flux data from here. So 8 times 264 flux value will be carried in here, in this. So what I wanna do, I wanna do like, I want OpenMC to collect data from here, from 8 individual of this position, then sum them and divide it by 8, as I can get a average flux value for each of this A01 assembly. So what I have to do, I have to say that mean dot sum. So after doing that, divide it by 8, no problem. Like if you don't give it like that, it will show your number. You see, this is a very small number. Actually this is normalized. This value is very small because this value is normalized. This is not multiplied by a normalization factor to get the real world flux value. Normalization, if you just multiply it by normalization factor, it just get converted to real world flux value. Should I show you the how do you calculate the normalization factor? No, let go. Just search ChatGPT and ChatGPT will let you understand, make you understand that how to calculate the normalization factor. It's a task for you, the viewers. Then I will take this data. Just first, I'm not interested with all the data. I will take this data from here and paste it in here. Let's say okay. So these are the flux value I got. Now if I say like power, like heating local, so it will do the same thing. It will do. So you see this value is very big. It doesn't matter. So what I can do this. Oh no. Yeah. So just paste them. So this is how you do that. Now repeat this for all the assembly. Like A01 is done, then what is the other assembly? A01 PC, right? And A01 PC, then A02, B01 PC, B02 PC. So what you have to do, you have to write like A01 and A01 PC, and this is heating local. So and this is another value. A01 and now A01 PC. Okay, bro. When I'm saying A01 PC, then this is actually in 4 places, not in 8 position. So what I have to do, I have to divide it by 4. So this is what I get. This is actual heating value. And where this A01 PC value assemblies, no.
Okay, I found this on the web for is there a one piece of all assemblies? No. Check it out.
Hey Siri, shut down. Hey Siri. Shut down.
Okay, nice talking with you.
Battery is low. What's wrong happening? Anyway, what I gonna do? Okay, A01 PC and A01 PC is in this position. Okay, I recorded this. Now what I have to do, I have to do this. I will copy and paste it in here. Paste it in here. Let's say this is for A01. So A01, this is it. For that, I need a new host. Let's say this is flux. Hey, let's do this just for hitting local. No, A01 PC, then B01 PC. Surely is okay. B01 PC and B02 PC. Okay, B02 PC and B01 PC is 8 times. Okay. So what I have to do, I have to do this B02 PC, B01 PC first. Okay. So what I have to do, B01 PC. So these values are actually normalized value, means the actual value is divided by the maximum values. Okay, B01 PC is done. Then let's go with B02 PC. Let's do this with B02 PC is done. Then C01 PC, no, maybe C01 PC, does this exist? No C01 PC. C01 hitting local, but this is for B02. Okay bro, B02 PC, and this is 4. Doing so wrong. What's wrong with me? So you see this, so B02 PC is done. Then C01, and there it will be 8. This is C01, this is C01. ঘাড় ব্যথা করতেছে রে ভাই, it's too long. Actually এই ভিডিওটা আমাকে ইউটিউবে যেখানে দিয়েছিলাম ওইখান থেকে রিকোয়েস্ট করছে। C02 okay, C02. Now C02, this is obviously 4 times, so this is, do this for, what's wrong bro? ফ্লাক্সের জায়গায় আমি যে পাওয়ার ভ্যালু বসাইছি, মানে কি মূর্খ নাকি ভাই? মূর্খ নাকি? This is it. Then C03, no 4. This is 1. Do you see the maximum flux generated in whole core? Not maximum flux, this is the maximum power generated in the center of the core. A02, I think A02 has no PC farm, only this. this doesn't exist. Alhamdulillah. A02 PCB4. So this is what we get. And this is A02, 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 and for A02. So calculating the power, normalized power value per assembly of the core is done. Now it's time for calculating the flux. So how do you do that? I say flux, ux flux, and this is A01 assembly, and this is 4. Okay, you see A01 is
okay.
no.
I found this on the web for
Shut
801.
down. Hey Siri.
Check it out.
Siri. Hey Siri. Shut down.
Until next time.
Yeah, shut down. So this is A01. This is A01. This is A01. This is A01. Now for A01 PC, what do I do? I say this. And then A02. Oh God. Shut down. Just don't talk. Hey Siri. So this is for A02. Where is it? This is in here. Very inaccurate values, because I already told you our batch number, inactive batches, active batches, particles, so it's very minimum. Okay, A02 and B01 PC, and B01 PC is like this. So B01 PC, and this is it. So this is B01 PC, and then B02 PC. But B02 PC, this is before. This is for C01, and this is 8. It should be 8, and this is Procare. So this is C01. So C01 is here. C01, then C02, and this is of course divided by 4. C02, C02, then not, yes, and this is the last actually. This is first C03. So done. So this is normalized flux. Normalized. Normalized. Okay, so this is all for today. I hope you guys enjoy the course. You guys didn't enjoy it, but thanks. In next video I will go like I will show you something more interesting that me and my the people I know, like they do something very cool things with OpenMC. Using OpenMC they do very cool stuff, and I think from the next video I will show you something more cool videos, and of course my core geometry and other stuff I will post them in my following post. Okay, I will attach them. So that's all for today. Allah Hafiz, and sorry if I killed your time. Allah Hafiz, tata.